first part of this video, we're going to have a look at two important tests for measuring the properties of materials: the tensile test and the impact test. The tensile test is important because by applying a simple uniaxial force, we can measure a range of properties which can be used directly in design and manufacture, like the elastic modulus, like the yield stress, like the tensile strength or fracture stress, and for manufacturing, properties which reflect the ductility, like the elongation and reduction of area. Here's a typical tensile test specimen. This one's made of mild steel. The important feature is this uniform section in the middle, the gauge length, which has a constant cross-sectional area so that we can convert the forces applied into stresses on the material. The two thickest sections are for holding in the grips, so we can transmit the force. And the radius regions here at the shoulders are to avoid unnecessary stress concentrations, because we want the specimen to fracture somewhere along the gauge length. Of course, before doing the tensile test, we have to measure that area accurately, and we also have to put some marks on if we want to measure the elongation after the test. It's no good making those measurements after we've deformed the metal. Now here's the tensile testing machine. The specimen is held between these two hydraulically operated grips. The lower grip is pulled downwards through this piston by a hydraulic actuator, and built into that there's a linear transducer which measures very accurately the displacement of the lower grip. The top part of the specimen is held in the upper grip, and the force being applied is measured by this load cell here. The output from the load cell and the linear transducer are fed onto this screen, and the load is being measured here in kilonewtons, the displacement in millimeters. But for our test, we're not going to use that screen. We're going to plot the results directly with this XY recorder, where we're going to plot the force on the vertical scale and the displacement on the horizontal scale. Well, we've got the specimen, the machine, the recorder. Let's go. Now the initial part of the extension is elastic. Let's see if it's recoverable as it should be. Yes, there you are, see the specimen's contracting down the same line. Let's continue. Now this is a steel specimen, and steel will yield, and it often shows a little drop called the yield point. Steels and only a few other materials behave like this. Ah, there it is. We've come to the end of the elastic region, a slight jiggery motion as the steel yields. Now it begins to work harden in the usual way. The material is now deforming plastically. And if we take off the load, it should return down the same slope of the elastic curve, but when it gets back to the zero force axis, we've got a permanent displacement. So that shows the permanent deformation that's occurred in that part of the curve. Right, now when we reapply the load, the yield point is of course a little bit higher than it was originally because the metal has work hardened, and it will now pick up the original stress strain curve the specimen is still deforming plastically. The rate of work hardening has reduced, and we must now be very much in the region of the maximum load. In fact, the load is just starting to fall. I think the specimen must be necking. In the gauge length now, somewhere a neck is forming, and we've lost the uniaxial stress situation, and a triaxial condition is now beginning to appear near the centre of the specimen. If you look at the gauge length now, you'll see that it's beginning to waste down as it now starts to concentrate the deformation in the one region. The load continues to fall because it's now acting on a smaller cross-section. And as deformation continues, so more and more of the deformation is confined to that neck, and eventually the specimen is going to break there. There we are, the end of the test. The bang that you heard, by the way, was the sudden release of the stored elastic energy as the specimen fractured. Well, we've got a good force extension curve, but the test still hasn't finished because we haven't got any parameters that tell us about the ductility of the material. So the next stage is to take the broken specimen from the grips and measure the reduction in cross-sectional area and also the elongation. Now, reduction in cross-sectional area is obtained quite simply by measuring the diameter, working that out as to the area of fracture, subtracting that from the original, so we know the difference, and then dividing that difference by the original cross-sectional area and expressing it as a percentage. The higher the reduction in cross-sectional area, the greater the ductility of the material. But of course, that's reflecting the deformation in the neck region. A different property which tells us about the material's ductility is the elongation. And we get that by measuring the extension of the gauge length. Before we test, we put two centre pop marks on the specimen, on the gauge length, at 50 millimetres spacing. To measure the elongation, we very carefully replace the broken pieces and measure how far those pop marks have increased. We're running up now, it looks like 58.49. Let's call that 58.5. That means it's extended by 8.5 millimetres on a gauge length of 50. On a gauge length of 100, that would be 17 millimetres extension. So the elongation value is 17% on this particular test piece. Now, the actual measurement of the elongation value is quite straightforward. But to get a meaningful value, we have to be very careful about the length of gauge over which we measure it in relation to the cross-sectional area of the test piece. And to understand why, I want to show you a test piece made of exactly the same steel, of the same cross-sectional area, but very much longer in gauge length. Now, if we replace the broken end, you'll realise that it only broke in one place. But the elongation is made up of two components. There's the elongation locally associated with the formation of the neck at the top here, but we also had the uniform elongation spread over the entire gauge length before the neck began to fall. Now, both of those contribute to the final extension of the test piece. If we were to measure the elongation over just the narrow region on each side of the neck, we should get a much higher value than if we measured it over a long test piece like this, simply because the necking elongation is then diluted by being divided by this length here, which didn't neck. And I've plotted a graph, in fact, to show how on this test piece the elongation value would vary according to the length over which we measured it. On the left are the high values dominated by the neck, and towards the right the curve flattens off due to the uniform elongation of the gauge length. So you see, we can have any value we like, from the highly localised extension associated with the neck to the uniform elongation of this part of the gauge length here. By international agreement, the gauge length measured for elongation is 5.65 times the root of the cross-sectional area, or some other figure which must be quoted beside the elongation value. And that's what we did with our original test piece when we measured our value that you saw being measured. Now, when this test piece fractured, it's occurred in two distinct stages. The first stage of fracture is a crack deep within the neck at right angles to the axis of the specimen, which gives rise to a flat fracture. But then as that gets toward the outside of the neck, so it changes direction and becomes 45 degrees shear. And so the outside is a 45 degree shear lip On this particular test piece, half the lip is on this side of the fracture and the other half is on that side. Sometimes the lip is continuous around one side of the fracture. When that happens, you can easily see why it's called a cup and cone fracture, because we have a cup shape into which fits the cone on the other side. With a rectangular specimen, you get a similar effect, but the 45-degree lip follows the shape of the rectangle. But it's an indication of a ductile fracture in tension. We get the strength values from the load extension chart. We know the original cross-sectional area of the specimen, so if we read off this point where yielding began, it's 45.2 kilonewtons, and that works out at 575 meganewtons per metre squared. We then take the maximum load, which is 48 kilonewtons. That gives us, divided by the original cross-sectional area, 611 meganewtons per metre squared. Now, if we want to, we could also measure the breaking load and divide that by the area of the fracture, and that would give us the fracture stress. Although normally, that's not recorded when we're expressing strength properties. It's a useful thing to know. Now, the problem arises, how do we get a modulus from the slope of this curve here? The problem is that when I told you about the machine on which we did this test, I said that the displacement was measured from the piston which pulled the crosshead down. Now, the trouble is, to get an accurate value of Young's modulus, we need to measure the extension of the gauge length, not of the shoulders and other parts of the machine which may be in the same load path. So how do you suppose we can do that? Well, the answer is to use a sensitive extensometer attached to the uniform part of the gauge length. Right, well, here's the specimen set up for your test. We want you to plot the force extension diagram. We've got the extensometer attached to the gauge length, and it's covering a 25mm length of the parallel gauge portion. You need to know the cross-sectional dimensions of the test piece. It's 20.0mm wide, and it's 9.2mm thick. We've put top marks at 80mm spaces so that we can measure the elongation afterwards. The output from the extensometer is coming up here on the screen on the displacement marker. We've got a slight problem with our computer program in that the second decimal place won't show up in the early part of the strain, which of course is the important bit for the modulus. So we suggest you measure your modulus from the 0 starting point up to the elastic limit. The load, of course, is coming up in kilonewtons with no problems at all. Right, well, we're ready for the test, so now you're on your own. Right, well, that's the specimen broken. Now let's measure the reduction area and elongation values. Here's the width and the thickness. Now for the elongation. Remember, the puck marks were originally 80.0mm apart. If you refer to your video notes, you'll see what we want you to work out from this test. And now here's George to show you what happens when we do tensile tests with plastics.
Plastics differ from metals in two important respects. First of all, their values of elastic modulus and strength in general, tend to be significantly lower. And secondly, the mechanical properties are time dependent. Here I have a specimen of an injection molded polypropylene. It's black because it contains a UV stabilizer. And we're going to see what happens when we test it at two different extension rates. Here's a specimen set up in the machine. Same specimen measures 28 millimeters in width, 3 millimeters in thickness, and we're going to test it at an extension rate comparable to the one you saw the metals being tested at earlier. Right, Jim, let's go. You see it extending. And there's a neck just starting to form about the centre of the gauge length. And you see that unlike the metals, the neck extends. And extends. And continues to extend. In fact, it extends beyond the extension range of the machine. So to show you what happens at the end, here's a specimen we tested earlier. You can see its elongation is very much greater than the elongation we had in the metals, of the order of a couple of 100%. And also, the fracture up at this end is fibrillar, which is due to the very high degree of orientation of the material. Right, let's see what happens when we test this material at a fast rate of extension. We're going to test it at an extension rate about 100 times faster. Notice the greater stiffness in the faster test. The specimen broke at the maximum load, which was higher than the yield load in the first test. The dropping trace is due to the continued movement of the actuator. A completely different mode of failure. Compared to the slower test, there's no necking, there's no elongation, and the fracture is completely brittle. What happens to plastics if we go to even longer timescales? Here's a specimen being prepared at an industrial laboratory for a different kind of tensile test, a tensile creep test. Here we see the extensometer being fitted. The specimen will be put under constant load and its increasing extension with time recorded. Because these tests are long-term, lasting a year and more, and are then used to extrapolate to even longer times, a high degree of accuracy is required. The extensometer is an optical one. It works by mirrors rotating the reflection of a light spot as the specimen extends. The specimen is placed in the grips of the creep machine. There are the lower knife edges of the extensometer, and there are the upper ones. It's the relative movement between each pair of lower and upper knife edges which rotates the mirror. The machine applies a dead weight to the specimen through a 5-to-1 lever arm. When the weight is released, this light spot from the extensometer moves, at first rapidly, and then slowing down. Readings are converted to strain values. Performing such tests allows us to produce curves such as this, which show the tensile creep modulus of HDPE as a function of time. From very long timescales to the very short, in a different type of test.